Hey guys, welcome to System Design Fight Club. I'm going to try to do a quick run through of the hotel reservation problem. Some background on this problem, where you can find some resources on it. You can find some really similar content to this problem scenario in Ticketmaster and the grokking material. This problem is covered in Alex Schu's second book. They just have the hotel reservation problem there. He also calls out that there's a lot of very similar ones. Digital Wallet has some really nice material that has a lot of overlap with this, since it's also a strong consistency problem. It actually includes a chunk on Raft, although I'm not actually a big fan of how Alex Shu covered it. It still felt really abstract in the way that he handled it. Anything that involves where there's a limited inventory and you're having them make a payment is going to be very, very similar to this problem. And then the other one is Design Airbnb, which is crowdsourced hotels. And then if you want to go really deep into your research on this and consistency overall, here are some great white papers for that. There's the Spanner white paper, which is Google's custom database solution that uses an LSM tree and has the TrueTime API. There's the Chubby white paper, which is on their distributed locking service. There's the Raft white paper. Paxos was viewed as really complicated, and so Raft is a more simplified distributed consensus algorithm. For Spanner, there's an open source implementation of it that's basically a clone. It's CockroachDB. For Chubby, the knockoff in the open source world is Zookeeper, actually. Okay, some call outs. This problem is very common in Square from what I've heard. I'm pretty confident it's testing your ability to handle a distributed transaction and partial failure scenarios, which is it really makes the content out there kind of embarrassing. The grokking material really cops out and keeps the scale of the problem restricted so that it can just do all the distributed transactions on one machine. It gets really tricky when you go large scale. And so that's what makes it really disappointing, that the content out there is kind of lacking. We can move on to functional requirements, but I don't plan on copying out like them. I do actually want to do a distributed transaction in this problem and cover a couple of approaches to it. Let's move on to the requirements and start to move into actually digging into this problem. So functional requirements, customers should be able to view available rooms. Customers should be able to make a reservation of a room. The people at the front desk should be able to view your reservation info for when they're like checking people in. There's a couple of approaches to this aspect of the problem. Is that Alex Shu designed it for 10% overbooking to be like baked into the design. It makes it a completely different approach than if you prevent double booking. And in fact, one of the similar problems is airline ticketing. And in the airline ticketing industry, it's actually illegal to do double booking or overbooking. So if you have that variation of the problem, you cannot actually do overbooking, which used to be common in the airline industry, but it's actually illegal now. You can't do that. I'm going to be taking this approach. I don't like baking in the double booking into the problem. I'll probably take the overbooking approach as a second approach to the problem, but I'm going to do the initial approach where I don't have double booking allowed. Non-functional requirements, like I said, we're going to do high consistency here, no stale data allowed. So that means that our availability is going to take a little dip, but it is high consistency. That's just one of the consequences of requiring high consistency. Out of scope, we're not really going to handle dynamic pricing. We're not really going to deep dive into the check-in process. We really want to focus on the reservations itself. External payment processing service. I think I'll kind of touch on that a little bit, but I don't want to dive into it too much. It's a little bit tricky, and I think it's usually just left off. I hate copying out on stuff, so I'm gonna at least touch on it. Because I don't like that the whole external payment processing thing is not covered, where you need to actually handle the transaction on their credit card with like Stripe, PayPal, or Visa and MasterCard. And it's tricky since it's an external service, and so you can't treat it like it's a database that you own and do the whole two-phase commit thing. So some numbers, back of envelope calculations. We're going to say that we get 3 billion page views per month, and that we have 30 million reservations per month. That's a 100 to 1 read to write ratio. call that a click-through rate, 1%. So for every 100 views, you get one person that actually clicks the buy button and actually places an order. This is roughly what the other resources out there were using for their click-through rate. Okay, so how many reads per second and how many writes per second? This is for capacity planning. So how many reads? We get 3 billion reads per month. So we're going to do 3 billion divided by 30 will get us reads per day. So that is 3,000 million divided by 30, which is equivalent to 1,000 million divided by 10, or 100 million reads per day. Well, we want how many per second, so we're going to do 100 million divided by 100,000. That's the number of seconds in a day. Will get us the reads per second. So that is equal to 1 million divided by 1K. So that comes out to 1,000 reads per second, which is a pretty fair volume. That's fairly high. How many writes per second? So we have a 100-to-1 ratio, so you can just do the math. It's going to come out to about 10 writes per second. You can go ahead and walk through all of it anyways. 30 million per month. So we have 30 million divided by 30 days a month. That's 1 million writes, 1 million reservations per day. 1 million divided by 100,000 seconds in a day. It's going to come out to 10. So the other resources had this number coming out to around 3 or 4. It's trivially easy to handle that number of write operations per second for a database running on a machine. And so then you're able to cop out and you're able to say, well, look, we can just stick all of our tables just on a single database. And then we don't really have to worry at all about distributed transactions and all that. I guess the leader follower pattern would actually be really useful here for scaling up to that number of reads off the same table, but I want to handle the distributed transaction fully. So let's go ahead and jump into the graph. We're going to have 2 browsers that I'm going to draw, and they're both for the customer. So we're going to have the browser for customer viewing listings, and we're going to have the browser for the customer making reservation. And both of those are going to have their own backend microservice. So we are going to have the listing service, and we're also going to have the booking service. And then we're going to need to have our data stores. So I'm going to have an inventory database. We want to know how many rooms are available. And then we're going to have the actual reservations as well. So B for reservations. And then we're going to have the listings. We're going to have the inventory DB. And then we're going to have our reservations DB, which is for when they've made their actual payment. Okay, so you have a request come in. They want to see what rooms are available. So this is going to go ahead and fetch that from the inventory. The inventory is going to give you a listing that meets the criteria that you're searching for. And then you're going to go ahead and you're going to show that to the customer. Okay, and so that is happening at 1000 TPS. And then they see a room that they like after browsing for however long. They're going to click the buy button, and that is going to, it's going to need to update the inventory. And we're also going to want to add an entry into the reservations DB. So how this was working in the other ones, in the other resources, is that we just kind of had these both as the exact same database. So instead of having 2 like we have right there, they just draw 1, and they're like, well, it's 1, you can just run it as a transaction. And then I'm going to quickly cover what I was talking about with the read, with the leader follower pattern, is that so we have 1000 TPS over here on the reads, and then we had 10 TPS on the write operations. These are write operations, so the data is flowing from here out to here. These are writes, and then that one is a read. And if you wanted to do the leader follower pattern for scaling it up, you would have your leader, and then you would have a bunch of follower nodes, and then you would just have your write operation running directly against this. You do your writes against the leader. Your writes always have to go against the leader. And then you would also synchronously replicate it out to all of the followers. So this is the leader. And then you have the followers over here that you're replicating all the data to. So the data is going to flow from the leader out to the followers. And then when you're doing that 1000 TPS of reads, you're just going to serve them right off of this. And so that's how you scale up the reads just fine. But if you're handling a non-trivial amount of writes, this is going to break down, and you're going to need to start out the leader. And then when we're talking about having multiple tables like that, you can't really do partitioning when you have multiple tables on the thing. It breaks down, and you just need to split it into two different. You have to do federation, is what this is called, where you have two different databases that serve different purposes. It's where you move your tables into separate data stores completely, and they can even use different technologies. Like you can have one that uses Elasticsearch and the other one uses DynamoDB and stuff like that. But anyways, if you this is one approach where you just scale up the reads on their own. I don't like this. It still is kind of copying out. I want to handle distributed transactions properly. But that's one way where you're just scaling up the reads on their own. We're not going to do that. Anyways, as you can see here, we want to do 2 writes. Why is that an issue? Why do we need to do a transaction in the first place? What is the issue with that? Well, I will go through, the issue is partial failure scenarios. I'll go through what's going on here and why we can't just do the 2 writes separately, and why we need to do a bundled distributed transaction here. So 1, we receive the request from the customer. 2, update the inventory. 3, update the reservations. 4, return response to the customer. So what happens if the node fails right between step 2 and 3? That means that you've updated the inventory, and then you still have a 400 or 500 error that returns to the customer. You've either timed out, or you've so if it's a failure on the node, it would be a 400 because it would time out and you're not getting a response back. If this itself failed, the step 2 itself failed, or step 3 itself failed, as in the nodes, the database nodes are experiencing an outage, you'd return a 500 error, because this is going to recognize, oh, hey, I'm experiencing an issue. We'll be able to communicate it properly. But either way, if you have either the node failing between 2 and 3, as in you've properly updated the inventory, but then the node itself goes down before you send anything over to the reservations database, or your write to the reservations DB fails, as in this node itself is experiencing issues. So that's either this thing failing or this thing failing at between 2 and 3, or on 3 itself. That's partial failure, and that would mean that you've updated the inventory, but you haven't placed the reservation, and so you've got this room that's booked, but you don't have anybody that's actually paying for it. And so you've got these like locked rooms that are not actually returning revenue. If you flipped these instead and you had your reservations coming first, that would mean you charge them, and then you would actually be able to get a double booking in the inventory. And so if this was the airline ticketing problem and you had it in that order where it was the reservation first, that would cause an illegal situation that would put you into hot water with your regulators. So this is what I'm talking about with partial failure scenarios. This is why we need distributed transactions, that we don't want to be in the situation where we have one succeeded and the other one failed. We want it to, the trick to partial failures is you either roll them forward to completion, or you roll them both backwards to undo them both. And that's what we want. And so one of the approaches to this is two-phase commit. It's just a naive consensus algorithm where you have the booking service itself is going to serve as the coordinator. And so then in step one, you're going to get both of the nodes to commit. And then in step two, you get them both to actually do the transaction itself. We're going to copy it. And then we're going to do that. And then we'll do 1, 2, 3, 4, 5, 6. And this is actually written into like the API of a lot of database software. So PostgreSQL, for example, it has an actual thing where you can do a prepare statement, and then you can tell it, hey, do the commit. So you're going to receive the request, and then you say, hey, do the prepare thing, which is where it locks the records so that nobody else can do the write while it wants to do the transaction. And then it talks to this one. It says, hey, lock your records for this transaction. After doing both of those, it then talks to this again. It says, okay, do the actual transaction, tells this one, go ahead and do the actual transaction. They should both complete successfully. Otherwise, it goes back through and it just rolls it back on both for the way that two-phase commit works. And then it returns whether or not they are both successful or they both failed back to the customer. This is naive because what if the coordinator fails? So you handled the issue of whether the database nodes themselves fail. That works just fine with this. But what if the coordinator fails? That's the issue here. That's why it's a naive algorithm. It's because you have a leader, a single node leader, and you're not replicating your transaction log anywhere. Two-phase commit is still good enough at a lot of companies. It seems like I've actually seen, I've heard of two-phase commit actually being used at Amazon.com and in scenarios where there's like 1,000 TPS for write operations. A little bit shocking why it's naive is that if the node fails after doing prepare and before you do the commit, then these records just kind of stay permanently locked. That's why it's naive. It does not actually fulfill the termination property of consensus, is I think how it's worded. It doesn't. It's not guaranteed to actually terminate the whole algorithm. Apparently, still good enough at Amazon.com. But a better way to do it is where you're using one of those more sophisticated things like Paxos or Raft. And unlike two-phase commit, where you're able to write the code yourself in your service, you should probably not roll it yourself, because that is it's kind of like with crypto algorithms. You don't want to roll your own encryption or anything like that. With two-phase commit, it's simple enough that you can go ahead and roll it yourself. With those more complicated ones like Paxos in particular, you don't want to really roll it yourself. You want to outsource it to something. And so actually in the book DDIA, it has a little section where it explains that you can actually outsource the code to Zookeeper. So I brought up before that, hey, you could check out Chubby, the white paper for Chubby, and the open source knockoff of Chubby is actually Zookeeper. So we're going to be using that. We are going to be using Zookeeper. We're going to outsource it to Zookeeper, which is going to be a distributed coordinator for us. It's one of the things that you may see Zookeeper advertised as is a coordination service. Notice that we have the word coordinator right there. Zookeeper is going to be our coordinator. You run it on multiple nodes. It replicates the transaction log, I believe, across the nodes running it. So you're gonna have a couple of machines running Zookeeper. If the one that's coordinating it fails, then one of the other nodes will just pick it back up and it'll properly drive the partial failure scenario either forwards or backwards. So that was the issue with two-phase commit, is that there was when the node fails, there's nobody to drive it forwards or backwards. But with Zookeeper, since it's distributed across multiple machines, when one fails, there'll be another one that'll come up to drive it through to completion. And so this one is going to talk to Zookeeper, and this is no longer a coordinator. And so what's going to happen is that your request comes in, this guy talks to Zookeeper, it says, hey, run the transaction. It has some nodes, it'll figure it out. It gives a response back of hey, I've succeeded, or hey, I failed, and they'll communicate to the customer, thumbs up or thumbs down, 500. We didn't charge your card, we didn't decrement the inventory or whatever. That's one of the ways you can do a distributed transaction. That's the less naive way. And I have not actually seen anybody actually running Zookeeper, which scares me because two-phase commit it can definitely lock up your records, and it does actually still have a bad partial failure scenario. It's rare, but it can happen. And you just have to throw a couple extra machines into your mix to get this full proper consensus algorithm to work. All right, let's keep going along. We also want to have the front desk people that are viewing the reservations. So after it's captured in here, we also want to have the browser for the front desk people. And that's, of course, going to talk to a backend as well. So it is the admin backend service is what we'll call it. They say, hey, somebody's checking in. Can you show me their info and confirm that this dude is not just trying to score a free room or something? And then it goes and talks to, and it looks at the reservations. We get the data back. We're doing a read, and it displays it into the browser. There we go. We got our system from end to end. Okay, let's talk about the schema a little bit. Depending on which of the two approaches here that you're using, it's going to affect the schema a little bit. And then also if you get a interviewer and you're going for a bit more senior role, or the interviewer just feels like busting your balls or something, they might bring up this thing called thread contention, and just be ready for that. It's that's a call out, is that when you're doing locking or something like that, it's depending on how you set up the records, they might bug you about thread contention or something. We're going to go over the inventory database schema. So we want to have I want to have the building ID, and then we're going to have the room type ID. Is it a king room? Is it a queen size room? Does it have a pair of queen beds? We're going to have the date of the reservation, the date where the rooms are available or not. We are going for the no double booking approach first. So we're just going to have is available, and we're going to have the individual room ID. So this is flattened where every single room and every single hotel has its own record. And it'll have a flag for whether or not it is reserved. And so when it's doing this, it's just going to set this to, it's going to flip it from true to false. And then we're also going to record the price here, at least for now, because I don't want to have dynamic pricing in scope. So room type ID, we'll say double, it's like 2 beds or something. Let's say that the current date is 10/6/2022. We're just going to have the day because you have reservations for a night, not like a specific hour or anything like that. So day is just fine. And we'll have the room ID. It's like the room number. We'll say it's room 201. Is available, true, price $200 per night. And that should actually probably have it as a string, because dealing with money and floats, it's a bad idea. So we're going to have it set up as a string. Okay, reservations DB, you're just going to copy the entire, this will be our primary key. That's our primary key right there. And you're just going to copy that into the reservations DB. Just going to have your full primary key. And then you're going to have your payment info flattened out. And you could also have the booking person information. So it could be name. We're going to say Albert Einstein is staying at the hotel tonight. That'll be the reservations DB. Okay, we can talk about the scale. Oh, we could talk about how we want to do the partitioning and the sort key. So we already talked about the primary key, but that's not the partitioning key or the sort key. The primary key is the made out of the partition key and the sort key. So when you're doing, when you're looking for a place to stay, you're going to look at settings for, you're going to specify a date. You would specify a type of room. You would maybe know what building it is. You'd also want to look at the price. So the price is actually also going to be a secondary index. I'm going to set up a secondary index on that. Is a bit, you want to filter it to rooms that are available. So you're also going to have secondary index for that. How are we going to partition it though? It's, you're probably going to want to look at, you'd have specific, so how is the key range filter going to work? You'd want everything to be in the same building. You'd maybe look at a specific building so you can partition it by the building, and then you can sort it by, I think you would want to partition it by the building ID and room ID, and then you can sort it by, you'd have it filtered to the room type, and you can also sort for the date. I don't think you want to partition it by date because then you're going to have a hot partition issue. So that is going to be part of the sort key. And the room ID, I don't think they're really going to care about that. So it would not, you're going to want that to be, that should be within a partition, I think. So that should also be part of the sort key. Okay, and so that's going to be part of the partition key, or you definitely want to have, I think you might just need the building ID for the partition key. Or, well, then you could have a hot partition from a specific building. So you maybe want to have a combination of the room ID and the building ID for forming the partition key. And so then you don't just have the one building across all the partitions. Yeah, so you can go ahead and use this as part of the partition key. This is a little bit more interesting of a partitioning issue. You're usually not going to get grilled on the partitioning key and sort keys, I think, particularly for this problem. Whenever there's a problem that has a really pronounced celebrity issue, they're probably going to bug you about the hotkey issue. You could probably get a hotkey issue off of the building ID. There might be specific hotels that have that are really popular for certain days or for certain events within a certain city or something. So you can get some hot partitioning issues going on this, I think. Okay, I don't want to focus, the focus I want on for this video though is on that partial failure scenario. So we'll just go ahead and move on. Let's talk about capacity planning. So I did already talk about the rights. You're only getting 10 TPS here. We literally only need 1 or 2 machines, maybe just a second, just so that you have a failover. You just have a backup over there in case the first one goes out for whatever reason. It's just a bad node. So I think it's good to usually have I've heard N+1, you have N machines that are sufficient for handling exactly as many transactions as you want. Then you add 1 extra machine just in case one becomes faulty for whatever reason. Listing service though, that one's getting 1,000 transactions per second, 1,000 reads per second. And I don't think it's going to be bandwidth bound. That one, we'll say it can handle, it's probably going to be CPU bound. And then it's like, how do you estimate that? And so it's probably going to look a lot more like 10 machines for handling the volume that you need. Okay, let's look at these. What technologies do we actually want to use for our 2 databases? So now that we are using 2 different data stores entirely, they actually don't have to run on the same technologies. You could have one that's Postgres, another one is like DynamoDB or something like that. So this one's actually going to have about balanced reads and writes. So you're going to get a write every single time that somebody makes a reservation, and a read at least when you're checking in, probably. It's low on both. You probably only need like 1 or 2 machines over here. I didn't like that this was such a cop out that it's only 10 TPS. So if we had maybe 1,000 TPS over here as well, and it was still balanced, I would say you could use Spanner here. It could be a nice use case to use. So you could use you definitely want strong consistency. You need strong consistency in this case since we're doing transactions. And we're not doing high availability. We definitely need strong consistency. Spanner definitely does that. Cockroach DB definitely does that. Or you can use DynamoDB with strong read consistency. Another option is PostgreSQL. If you get a stare from your interviewer and they're like, you're handling this for a stupid amount of scale, and I really do want this to only handle 10 TPS, then you can be like, yep, PostgreSQL, that works great here. But if they are bugging about scaling it, that's when you can talk about Spanner, CockroachDB, DynamoDB with strong read consistency. I think this provides enough. It bothers me so much that they name it strong read consistency, which is clearly they mean this is not strong consistency, this is strong read consistency, which I think probably is like read your own rights consistency, which would still be good enough for our use case since we just want to avoid having any stale reads at all. Okay, so those are some options over there. Yeah, I'm gonna go with DynamoDB with strong read consistency. That'll work fine. Spanner is actually really expensive. I've heard this is real expensive because of the true time API, which requires customized hardware. So DynamoDB with strong read consistency. And then for this one, we're getting 1,000 reads and then 10 writes. So this is super read heavy. So I really want a B tree over there. And so I think again, so I don't want to use Spanner or CockroachDB. I would want to use either DynamoDB with strong read consistency or PostgreSQL over here. I don't want to use Spanner. That's just totally unnecessary for this. Okay, so those are our database choices. What else do we want to talk about? Oh, okay. So this is how we would handle it if it was no double booking allowed. If we wanted to go a different approach, so we're going to go and talk about approach 2, which is when we want to allow for 10% overbooking, or you could call this like an alternative approach. So we want to allow for 10% overbooking. And so then it's you like, how do you know what room you want to double book? So we're going to drop the room ID. We're just going to have the room type, and we would have the capacity available, rooms, room count, room count. It's up to 200. Then we have rooms reserved. So let's say we've only got 5 so far. And we're going to drop is available. That's not what we need anymore. Or we could say, actually, there's a smarter way to handle this. Instead of rooms reserved, you would have rooms left. And that would be how we would avoid showing people unavailable rooms. If we just have rooms reserved, we would have to compare these two attributes, and we would return we have to do math on these two things and return the result of that to the listing service, as opposed if we have rooms remaining count. So we would say this one has 120 rooms remaining. And so you would only return results that have greater than 0 for this value to the listing service when you're showing it over here, because you don't want to show rooms that are not actually available. And so rooms remaining would be a secondary index. We're going to allow for double booking. There's 2 approaches that could either allow this to go negative, or you would just set this value to be 10% higher than it should be. So you'd say it's 220 when it should actually be 200. So that's how you could do 10%. I like that more, because instead of having this be some kind of dynamic number like -20 or -10 for determining whether or not it's available, you would be able to keep it at 0. And so for the 10% overbooking, I would just overset the rooms count instead of the rooms remaining count being able to go negative, because it keeps that rooms remaining cutoff for available or not at 0. Okay, so that's secondary index. Sort key, yep, because otherwise they're gonna need a hot partition off the dates. Room type, yeah, it can be a sort key. Building ID, that's, oh, okay, so then we're gonna get a hot partition issue possibly. I think we should just leave it. So that is an option with hot partitioning, is that you can just eat the hot partition issue and hope that it's not that horrifically imbalanced as it is with like Elon Musk on Twitter, where he's got like 10 million followers or something absurd like that. And you've got, your own account on Twitter with like 100 or maybe just 10 followers if you are like me and you don't actually use it. So I think in this case, it's not so imbalanced with the different buildings that your hot partition issue is actually going to result in some really nasty latency on one specific machine. So you can just eat it. If you can't, another approach with dealing with a specific hot partition is that you can take the hotkeys and then you would just do you would add, so you have the ID and then you add plus R&D and then you have it from 0. It's just a value between 1 and then however many partitions you want it distributed to. So let's say we want to split the traffic for the one building over 3 partitions. So you just do random between 1 and 3. And I've seen it go as high as it's like, I think it's really common to have it as 100 and then you just have it divided over 100 machines, or if you have like 20 machines and you specify as 100, it means that it's going to, you're just doing a hashing function here. So that's one way to handle it. It adds a lot of complexity. So it's not, it's a messy solution. It's rare that people actually like to do that. It's usually not the right approach. It's usually not the right approach. But that's one way to handle the hot partition issue. But I would prefer to just eat it here. You just sit on the, you just accept the hot partition issue in this case. Okay, what else do we want to handle? Oh, external payment processing service. Okay, yeah, I can talk about that. I want to do that on approach 1 just because I hate this approach so much. Okay, one more thing. I brought up thread contention. You can get an interviewer that wants to bust your balls on thread contention. So now you're squashing all 200 rooms into one record. And so then if there's a particular type, such as oceanfront at Four Seasons, then you're going to have a lot of people trying to access it at once, possibly. And so then that would be thread contention. They might try and bust your balls on that. That's a particular issue if you're going to take this approach, is that you could have a bunch of people trying to access one record at once. If the overall TPS is 10 or 3, I mean, it's just not pronounced enough that you're really going to get an issue. They could bring up a spike. So let's say they want to say 10 TPS average. That's how they like to say that. That's definitely how they would say, is that there's a 10 TPS average, and then on the really bad scenarios like oceanfront at Four Seasons, there could be like a specific time of the year where just people suddenly slap it at like 1000 TPS, where everyone's looking at it all at once for whatever reason. So then you're getting actually, let's say 100 TPS at the peak, and they're all trying to access just this one room type. And since it's all in one record, instead of flattening the rooms out into a few hundred, then you're going to get that thread contention where 100 people are trying to access the same exact record in the inventory DB all at once. And that's thread contention. That's what's going on there. You can talk about optimistic versus pessimistic blocking. I'm gonna say you should split the records out or something. Yeah, it's be prepared for that. If you're gonna do this approach, interviewers really like to bring up thread contention there. With this approach, they're all in different. There's a bunch of different rooms. They pick a random one. I don't think you're really at as much risk of contention over here. Let's move on to the next topic, which is external payment service. You've got this booking service, and when you're trying to make the reservation, you're going to have to decrement the inventory. You're going to have to add a record over here with your actual reservation. But then there's the actual payment processing. How do you know that it's legitimate card info that they entered? How are you going to actually charge their card and transfer it over to your bank account? You need a payment processor for that, and it's going to be an external service. So it's going to be external payment processor service. So common ones for that: Stripe, PayPal. Maybe you can talk directly to Visa or MasterCard if you're a big enough company. You might just go ahead and roll it yourself. That is another call that you would have. I don't know if your coordinator really needs to do that. So the way that external payment processors usually work is that there's like kind of two steps to it, is that first they place a hold on your card, and then two, they actually charge your card. So what I would do here is I would have the hold on your card happen before these. I hope that the hold has this like timeout to it. I haven't done a deep dive on how this thing actually works, but it looks like it would be a little bit like a two-phase commit, where this is kind of like the locking a record, the prepare phase. And then this one's like the actual commit phase where it does the charge. And when you're a variation of two-phase commit that's a little bit better is called three-phase commit, where the prepare phase has a timeout to it, I think is how it does that. The prepare phase can timeout. And so I'd hope that the hold has a timeout on it, where it's like after 2 days, if you didn't do the charge, then the hold's just going to disappear. And so here we're going to have step 2 is place the hold on the card. Then you go ahead and do your distributed transaction, and then you could go ahead and do charge card, do the actual charge. You can even have that happen downstream. You can have the charge actually happen downstream. So then you have this going on, and then you can even have a stream. You can have a stream, a message broker, and then this thing is subscribing to it and it's coordinating that transaction. And then, or you would have, I guess, a Lambda function and it would run that. Then you have this other thing that runs the charge. But anyways, place the hold on the card, do that stuff. The charge happens later after making this other stuff go through. But it's making this, make sure that the funds are actually there, and make sure it's a legit card. You can actually get the money off of the card. It's locking those funds on the card that you want to charge, like a prepare phase. And then the last one's kind of like the commit. It's actually driving it through. That's how I do it. Let's not have the broker there. Let's run it just like that. What I've seen at Amazon is that they actually place the hold for 30 minutes and they give you 30 minutes to cancel your order, and then they do the actual charge 30 minutes after placing the hold on your card. But you're still able to lock down the inventory, and your actual order does go through right away and the inventory gets decremented right away. But then you have a 30-minute window to cancel, and it'll drive these back within those 30 minutes if you try to do that. And then there's the charge that happens at the 30-minute mark. That's how I would do it with an external payment processor, though. It's really hard to do this since it's external. You can't actually treat it like an internal component. That just adds a lot of complexity. You can't talk to the processor and be like, hey, I want you to go set up this prepare phase, and I want to have this idempotent commit phase. So I hope the charge is idempotent, where you have the hold, and then you get an ID, a dedupe ID back from the hold, that you can use this ID to say like, hey, make sure this has actually been charged. So the charge would happen with a dedupe ID. I haven't actually done a deep dive on how payment processors work, but my hope is that that's how that works. Not a lot of people expect you to know how payment processors actually work, but this is how I would guess that it works. I know that there's 2 phases to it, though. I know there's this hold phase. I know there's this charge phase. Beyond that, I don't know a whole lot. Yeah, I think we've covered everything now. I'll go ahead and post this on the Discord channel and upload the video. Thanks for watching. I will see you guys later.